Welcome to this coding walkthrough. Today, we'll be exploring LeetCode problem number 667, Beautiful Arrangement 2. This problem challenges us to construct a permutation of numbers from 1 to n that satisfies specific conditions. Stick around as we break it down step by step and uncover an optimal solution. In this problem, we're tasked with constructing a list ARR of size n that meets two specific conditions. First, the list must contain all integers from 1 to n in any order. Second, the absolute differences between consecutive elements in the list must form exactly k distinct values. For example, if k is 1, this means all the differences between consecutive numbers in the list should be the same. If multiple solutions are possible, we can return any valid one. The input consists of two integers, n and k, where n is the size of the list, and k is the number of distinct differences required. The output is a list of integers of size n that satisfies these conditions. Let's look at some examples to clarify these requirements further. In the first example, we have n equals 3 and k equals 1. One valid output is the list 1, 2, 3. This list contains all the numbers from 1 to 3 in order, and the absolute differences between each pair of consecutive elements are as follows. The difference between 2 and 1 is 1, and the difference between 3 and 2 is also 1. Since all consecutive differences are the same, we have exactly one distinct value, which satisfies the condition for k equals 1. This example shows that when k is 1, the simplest solution is to arrange the numbers in sorted order. Now looking at the second example, where n equals 3 and k equals 2, a valid output is 1, 3, 2. This list also contains all the numbers from 1 to 3, but the order is different. Let's calculate the absolute differences. The difference between 3 and 1 is 2, and the difference between 2 and 3 is 1. These differences form exactly two distinct values, 1 and 2, which satisfies the condition for k equals 2. This example demonstrates how rearranging the numbers can help us achieve the desired number of distinct differences. In the third example, we have n equals 5 and k equals 2. A valid output is 1, 3, 2, 4, 5. This list contains all the numbers from 1 to 5. Let's calculate the absolute differences step by step. The difference between 3 and 1 is 2, the difference between 2 and 3 is 1, the difference between 4 and 2 is 2, and finally, the difference between 5 and 4 is 1. These differences form two distinct values, 1 and 2. This satisfies the condition for k equals 2. By carefully alternating between smaller and larger jumps, we can construct lists that meet the required number of distinct differences. It's important to note that the problem guarantees that a solution always exists for the given values of n and k. Additionally, there are often multiple valid outputs for a given input, so we only need to return one valid solution. Since n can be as large as 10⁴, the solution must be efficient, ensuring that we can construct the list within the given constraints. We also need to consider edge cases, such as when n and k are at their minimum or maximum values, and cases where k is close to n. With these constraints and edge cases in mind, our goal is to devise a simple and efficient approach to solve this problem. When solving LeetCode problem number 667, Beautiful Arrangement 2, the main challenge lies in creating a valid permutation of numbers from 1 to n such that there are exactly k distinct absolute differences between consecutive elements. One of the first approaches we might consider is the brute force method, where we generate all possible permutations of numbers from 1 to n and evaluate each one to see if it meets the condition of having exactly k distinct differences. This involves calculating the absolute differences between consecutive elements, counting the distinct values, and checking for the desired k. However, while this approach is straightforward to conceptualize, its computational complexity is a major drawback. Generating all permutations has a time complexity of O(n), which grows exponentially as n increases. For larger constraints, such as n up to 10 to the power of 4, this method is entirely impractical, and we must look for a more efficient solution. To overcome the inefficiency of brute force, a greedy approach can be employed, which focuses on controlling the placement of numbers to achieve the desired distinct differences. The intuition here is that by alternating between the smallest and largest in-used numbers, we can systematically produce the exact number of distinct differences needed. For instance, if we start with the smallest number, then take the largest, then the next smallest, and so on, we create a zigzag pattern in the arrangement. This pattern inherently maximizes the differences at the start and gradually reduces them, ensuring we achieve the required k distinct values. For example, with n equal to 7 and k equal to 4, we could construct a sequence like 1, 7, 2, 6, 3, 5, 4, which produces differences of 6, 5, 4, 3, 2, 1, exactly 4 distinct values. Once we've created the first k differences, the remaining numbers can simply be added in sequential order to complete the permutation. This method is highly efficient, operating in O(n) time, as we only need a single traversal to construct the result. Another way to think about this problem is through a mathematical perspective, which builds on the same principle as the greedy approach but focuses on the structure of the permutation. By alternating between high and low values, we can directly construct the permutation without explicitly tracking the differences. This streamlined process ensures that the required distinct differences are produced naturally as part of the sequence. Ultimately, the chosen strategy for solving this problem is the greedy approach. The key insight here is that the zigzag pattern of alternating between the smallest and largest in used numbers inherently generates the desired number of distinct differences. This approach is not only efficient but also straightforward to implement, avoiding the need for additional checks or constraints. With a time complexity of O(n), it scales effectively for large inputs, and its simplicity makes it a clear choice for tackling this problem. When we compare the greedy approach to the brute force method, the advantages become immediately apparent. The brute force approach, with its factorial time complexity, is simply not feasible for larger values of n. In contrast, the greedy method directly leverages the problem's constraints, allowing us to construct the solution efficiently and systematically. This balance between efficiency and simplicity makes the greedy approach the optimal choice for this problem. It avoids unnecessary computational overhead while adhering to the constraints, providing a clear and elegant solution. In conclusion, the greedy strategy stands out as the best approach, offering a practical and intuitive way to solve the problem while meeting the requirements effectively. In this problem, we are tasked with constructing a permutation of integers from 1 to n such that there are exactly k distinct absolute differences between consecutive elements. A key idea here is that the differences between consecutive numbers in the permutation determine its beauty. For example, if n equals 5 and k equals 3, the differences could be 1, 2, and 3. To achieve this, we need to carefully place numbers such that these exact differences are created. A powerful insight is to alternate between numbers from the start and end of the range. This strategy creates larger differences initially and smaller ones as we proceed. For instance, if n equals 6 and k equals 4, a permutation like 1, 6, 2, 5, 3, 4 achieves the differences 5, 4, 3, 2. This alternating pattern is the foundation of our approach. To construct the permutation efficiently, we start by focusing on the first k differences. Using the alternating pattern, we can generate these differences by alternating between the smallest available number, called low, and the largest available number, called high. Once the first k differences are created, the remaining numbers simply need to be appended in sequential order, as they will not introduce any new differences. The algorithm begins by initializing an empty list called result to store the permutation in two pointers, low starting at 1 and high starting at n. We then generate the first k plus 1 elements by alternating between appending low and high to the result. If the current index is even, we append low and increment it. If the index is odd, we append high and decrement it. After k plus 1 elements are added, the remaining numbers, which are now consecutive, can be appended directly to complete the permutation. Once the alternating process for the first k plus 1 elements is complete, the result array is almost ready. To better understand, let's walk through an example where n equals 6 and k equals 4. We begin with low set to 1, high set to 6, and an empty result list. In the first iteration, we append low, 1, and increment it to 2. Next, we append high, 6, and decrement it to 5. We continue alternating, appending low, 2, and incrementing, appending high, 5, and decrementing, and so on until we have added the first k plus 1 elements, resulting in 1, 6, 2, 5, 3. At this point, only one number remains, which is appended directly to produce 1, 6, 2, 5, 3, 4. Finally, we return this result, which satisfies the requirement of exactly k distinct differences. This algorithm is both time and space efficient. The time complexity is O, n, because we process each number in the range from 1 to n exactly once. The space complexity is O, 1, as we only use a fixed amount of extra space in addition to the output list. Let's consider a few edge cases. When n equals 2 and k equals 1, the only possible output is 1, 2, as there is only one difference. When k equals n1, the pattern alternates strictly between the smallest and largest numbers, such as 1, n, 2, and 1. For k equals 0, the input is invalid since at least one difference is required. By alternating between low and high values for the first k differences, and appending the remaining numbers sequentially, we ensure that the algorithm is robust and works efficiently even for large inputs like n equal to 10 to the power of 4. The provided Python implementation solves the LeetCode problem Beautiful Arrangement 2 efficiently using a two-pointer approach. Here's a step-by-step explanation. 1. Problem setup. The method construct array takes two inputs n, size of the array, and k, the number of distinct differences required. 2. Initialization. An empty list result is created to store the final permutation. Two pointers, left and right, are initialized to 1 and n, respectively. These pointers allow alternating between the smallest and largest numbers. 3. Create k distinct differences. A loop runs k plus 1 times to alternate between appending values from the left and right pointers. If the index I is even, the smallest value, left, is appended, and left is increment. If I is odd, the largest value, right, is appended, and right is decrement. This alternating pattern ensures distinct differences are created. For fill remaining values, after generating the first k plus 1 elements, the remaining values, from left to right, are appended in increasing order if k is even, or in decreasing order if k is odd. This ensures the sequence remains valid. 5. Return the result. Finally, the constructed array result is returned. The algorithm runs in O, n, time, as it processes each number from 1 to n exactly once. This approach is both efficient and simple, leveraging the alternating pattern to satisfy the problem's constraints. The code handles all edge cases, such as k equals 1 or k equals n1, seamlessly by design. Here, we begin by importing the necessary Java utilities and defining our solution class. The main method, constructArray, takes two parameters, n, which represents the size of the array, and k, which is the number of distinct differences we need in the arrangement. Inside the method, we initialize an integer array called result to store our output. Additionally, we define two pointers, left starting at 1 and right starting at n. These pointers will help us alternate between the smallest and largest values to ensure we create k distinct differences. The for loop iterates through the first k plus 1 elements of the result array. If the current index I is even, we assign the value of left to result, I, and increment left. Otherwise, we assign the value of right to result, I, and decrement right. This alternating approach ensures that the differences between consecutive elements are distinct, satisfying the requirement for k distinct differences. Once this loop completes, we have the first k plus 1 elements populated. Next, we handle the remaining elements of the array, from index k plus 1 to n1. At this point, the alternating pattern has already achieved the k distinct differences, so we simply need to fill the rest of the array in a sequential manner. If k is even, we continue incrementing the left pointer to fill the remaining indices in ascending order. If k is odd, we decrement the right pointer instead, filling the array in descending order. This ensures that the unused values are added without affecting the distinct differences already achieved. Finally, we return the result array, which now contains the desired arrangement with n elements and exactly k distinct differences. This problem requires us to construct an array with integers ranging from 1 to n, ensuring there are exactly k distinct differences between consecutive elements. To achieve this, we alternate between the smallest and largest unused values for the first k plus 1 positions, then fill the remaining spots in sequential order. For instance, with n equal to 5 and k equal to 2, we initialize an empty result array and use two pointers, left and right, set to 1 and 5 respectively. Starting with the smallest value, we alternate between appending the value at the left pointer and the right pointer. For the first few iterations, the result becomes 1, then 1, 5, and finally 1, 5, 2, as we increment the left pointer and decrement the right pointer accordingly. Once we've completed k plus 1 iterations, we fill in the rest of the array with values in ascending order, adding 3, 4, to finalize the result as 1, 5, 2, 3, 4. This process ensures the array contains the required k distinct differences. The output for the first example is 1, 5, 2, 3, 4. Let's look at another example with n equal to 6 and k equal to 3. Here, we follow the same process. We start by initializing an empty result array in pointers, with left at 1 and right at 6. Over the next k plus 1 iterations, we alternate between appending the value at the left pointer and the right pointer. The array evolves as follows: 1, 1, 6, 1, 6, 2, and finally 1, 6, 2, 5, while the pointers adjust appropriately. After completing these iterations, we fill the remaining positions. Since k is odd, we append values in descending order, resulting in 4, 3. Combining these, the final array becomes 1, 6, 2, 5, 4, 3, which satisfies the conditions of the problem. In a simpler example with n equal to 3 and k equal to 1, we again initialize an empty array with left set to 1 and right set to 3. This time, we alternate for only 2 iterations, as k plus 1 equals 2. The array develops as follows: 1, after appending the value at the left pointer, then 1, 3, after appending the value at the right pointer. With the alternating phase complete, we fill the remaining positions. Since k is even, we append the values sequentially in ascending order, adding 2 to the array. The final result is 1, 3, 2, which meets the requirements of the problem with exactly one distinct difference. The key insights from this approach are as follows: alternation between the smallest and largest unused values ensures we generate precisely k distinct differences between consecutive elements. Once the alternating phase is complete, filling the remaining positions sequentially completes the array. Whether we append these values in ascending or descending order depends on whether k is even or odd, ensuring correctness of the solution. This algorithm is efficient, running in O(n) time, as we process each number in the range exactly once. This simplicity and efficiency make it well suited for the constraints of this problem. To analyze the time complexity of our solution, we start by breaking it down into its main components. First, initializing the result array and the 2 pointers, left and right, is a straightforward operation that takes constant time, O(1). Next, we have the first loop, which iterates k plus 1 times, where k represents the number of distinct differences we aim to create. During each iteration, we append a value to the result array, and this appending operation is O(1). When you sum over all k plus 1 iterations, the time complexity of this loop becomes OK. Finally, we have the second loop, which adds the remaining n, k plus 1, values to the result array. Although generating the range for these values is efficient at O(1), the extend method iterates over the range and appends each value, giving this loop a time complexity of O(n) k1. Now, combining the contributions from both loops, the first loop takes OK, and the second loop takes O(n) k1. When we add these together, we have OK plus O(n) k1. This simplifies to O(n), as n is the dominant term. Therefore, the overall time complexity of the solution is O(n). Shifting to space complexity, the main contributor is the result array, which stores n integers, requiring O(n) space. Additionally, the auxiliary variables such as left, right, and the loop variable I are simple integers and consume only O(1) space. The range object used in the second loop is evaluated lazily, meaning it doesn't explicitly store all elements in memory, and thus it also requires O(1) space. These considerations demonstrate that the space complexity is dominated by the result array, making it O(n). When we sum up the space usage, the result array, which grows to size n, is the primary factor, leading to a space complexity of O(n). To compare this with a brute force approach, consider generating all permutations of the array 1, 2, n, and checking which ones meet the condition of having exactly k distinct differences. This naive method has a time complexity of O(n), due to the factorial growth associated with generating permutations. Additionally, storing these permutations would require O(n) space, making it highly inefficient. By contrast, the optimized approach avoids generating permutations altogether. Instead, it uses a greedy two-pointer strategy to directly construct the desired arrangement, reducing the time complexity to O(n) and the space complexity to O(n). This makes the optimized solution significantly more practical and scalable compared to the brute force method. The mathematical basis of the time complexity lies in the efficiency of the two-pointer strategy. The first loop, which ensures exactly k distinct differences, performs O(1) operations for each of its k plus 1 iterations. Similarly, the second loop, responsible for filling the remaining n, k plus 1 values, also involves O(1) operations per value. When these are combined, the total number of operations is proportional to the input size n, leading to a time complexity of O(n). This optimized solution leverages the best possible complexity for this problem, ensuring both efficiency and clarity in its implementation. One common mistake in solving this problem is misunderstanding the requirements. The goal is to create exactly k distinct differences, not just k differences. Some solutions fail because they allow repeated differences, which doesn't satisfy the problem constraints. Another frequent pitfall is using a brute force approach to generate all permutations of numbers from 1 to n and then counting the distinct differences. While this might work for small inputs, it results in factorial time complexity, which is completely impractical for larger values of n. Additionally, there's a tendency to mishandle edge cases, such as when k equals 1, where the output should simply be a sequential array like 1, 2, 3, n. On the other hand, for k equals n1, you need to maximize the differences. For instance, if n equals 5 and k equals 1, the answer is 1, 2, 3, 4, 5, but solutions aimed at maximizing differences might incorrectly shuffle the array. Lastly, some solutions overcomplicate the process with recursive or backtracking strategies, which can introduce unnecessary complexity and errors. A simpler greedy approach is often more effective and easier to debug. Another mistake is overlooking the constraints and failing to optimize the solution. The problem can actually be solved in linear time, O(n), by leveraging a pattern of alternating extreme values and then filling in the rest sequentially. For instance, if k equals n1, you can alternate between the smallest and largest in-use numbers to maximize the distinct differences. For smaller values of k, you transition to a sequential array after constructing the first k differences. This insight is key to developing an efficient solution. The greedy construction technique involves starting with extreme values, such as 1, yin, 2, and 1, to quickly create distinct differences. After achieving the required k differences, the remaining numbers are simply appended sequentially, which guarantees both correctness and efficiency. Furthermore, during interviews, you should be prepared to explain why this greedy method is preferable to alternatives like brute force or backtracking. It's also important to highlight edge cases that you've tested, such as the smallest input, n equals 2, k equals 1, the largest input, n equals 10 to the power of 4, k equals n1, and transition cases like k equals 1, k equals 2, or k equals n2. This problem shares similarities with several other problems on LeetCode. For example, LeetCode 526, Beautiful Arrangement, also involves arranging numbers under specific constraints. Similarly, LeetCode 31, Next Permutation, focuses on generating permutations with particular properties, which may provide insight into problem-solving strategies. Another related problem is LeetCode 1291, Sequential Digits, where you construct numbers or sequences that satisfy given constraints. Lastly, LeetCode 135, Candy, requires a greedy approach to distribute items under specific rules, which is conceptually similar to the alternating pattern used in this problem. Exploring these related problems can help you develop a deeper understanding of sequence construction and optimization techniques. There are a few alternative approaches to solving this problem, each with its own advantages and trade-offs. The most efficient method is the greedy approach, where you alternate between the smallest and largest in-used numbers to create distinct differences, and then fill the remaining numbers sequentially. This approach has a time complexity of O(n), and requires only O(1) additional space. It is both simple and efficient, making it ideal for competitive programming. Another approach involves backtracking, where you recursively generate permutations and track distinct differences. While this method can provide insight into the problem, it has a factorial time complexity, O(n), which makes it impractical for larger inputs. Finally, there's the mathematical formula approach, where you directly derive the sequence based on patterns. This method also runs in O(n) time with O(1) space, but it requires a deep understanding of the problem and can be less intuitive to implement compared to the greedy strategy. Each approach has its own use case, but for most scenarios, the greedy method strikes the best balance between clarity and efficiency. Great job making it to the end. To summarize, we explored a zigzag pattern approach to solve beautiful arrangement 2 efficiently. Remember, problems like this highlight the importance of recognizing patterns in constraints. Thanks for watching, and be sure to check out more solutions on this channel. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!